So again, if some event E has A favorable ways of occurring, then we say as opposed to B unfavorable ways of occurring, we say the odds of event E occurring would be A to B, and the odds of event E not occurring would be B to A. All right, a probability is a comparison between the number of favorable outcomes in a sample space compared to the total number of outcomes. If we're interested in getting two or less when rolling a single die, how many ways can we roll a 2 or less than 2 when we roll a die? Well, that would occur if we roll a 1 or a 2. So there are two favorable outcomes that favor the event of rolling 2 or less on a die, and there's 6 total outcomes when you roll a die. So we would say the probability of rolling a 2 or less on a die would be 2 divided by 6, or 1/3. Or in our minds, we know that to be about 33% chance. Now, odds are similar, but they provide a comparison between the number of favorable outcomes versus the number of unfavorable outcomes. So in the case of rolling a die and getting 2 or less, there are 2 favorable outcomes which would enable the event to roll a 2 or a less to occur, but there's 4 unfavorable outcomes which would not warrant that 2 or less is rolled on a die. Hence, we would say the odds of rolling 2 or less on a die would be 2 to 4, 2 to 4 odds, okay, or 1 to 2 odds if you reduce it. So the odds of rolling 2 or less on a die would be 1 to 2 odds. The odds of not rolling, the odds of rolling something larger than a 2 on a die would be a 2 to 1 odds. Is this making sense so far? All right, here's an example. A card is drawn from a standard deck of 52 cards. What would be the odds in favor of getting an ace? In other words, what's the odds of pulling out an ace out of a randomized deck of cards? Well, how many favorable outcomes yield an ace? Well, there's 4 aces. So there's 4 favorable ways of getting an ace, right? And there's 48 unfavorable ways of getting an ace. Therefore, the odds of getting an ace when we select a card at random from a randomized or well-shuffled deck would be 4 to 48, or 1 to 12 odds. So the odds of selecting an ace from a randomized deck would be 1 to 12 odds. So what would be the odds of not selecting an ace from a deck of cards? That would be 12 to 1 odds, or 48 to 4 odds. Okay, does that make sense there? What's the odds against getting an ace? Well, 12 to 1. Describe what these odds mean. It basically means that if you were to select randomly 13 cards from this deck of cards, we would expect to get an ace only once and to get a card that's not an ace 12 times. That's a way of interpreting what 12 to 1 odds means for not selecting an ace. Again, if we selected 13 cards from this deck, we would expect 12 of those 13 to yield a card that's not an ace, and only one of those cards to yield an ace. All right, now here's some important formulas that relate odds to probabilities. So the odds in favor of some event E occurring would be equal to the probability of that event E occurring divided by the complementary probability, 1 minus the probability of event E occurring. On the other hand, the odds against event E occurring would be the reciprocal of the above ratio. It would be 1 minus the probability of event E occurring divided by the probability of event E occurring. So these formulas relate odds to probabilities. So here's an example. The probability of getting exactly 1 pair in a 5-card poker hand is 0.423. Find the odds in favor of getting exactly 1 pair in a 5-card poker hand. Well, the odds in favor would be equal to the probability of getting a pair in a 5-card poker hand, which is 0.423, divided by 1 minus 0.423. which would give you 0.423 to 0.577. And if you simplified this ratio by multiplying the numerator and denominator by 1,000, this should be 1,000 here, ladies, I'm not 100. Yet another typo surfaces in these PowerPoints here. That should be 1,000 here. If you multiply the numerator and denominator of this ratio by 1,000, you get the odds of having a pair occur in a 5-card poker hand to be 423 to 577. So the odds in favor of getting exactly one pair are 423 to 577, and the odds of not getting exactly one pair in a 5-card poker hand would be 577 to 423 odds. Okay. Any questions about that?
I have one. So how did you know that that the 100 isn't the right thing? How do you know it was 1,000?
Because we want to turn these decimals into whole numbers. You see that? So we would have to shift our decimal point not 2 places to the right, but what? 3 places to the right.
Okay.
That's why I got to multiply top and bottom by 1,000, not 100.
Okay.
Right. Yeah, if you just multiply top and bottom by 100, you'll have 42.3 to what? 57.7, correct? And we don't like to have decimals or fractions appearing in a fraction or a ratio. And it should, therefore, we would multiply top and bottom by 1,000 to turn both these into whole numbers in. Okay, that's what's going on there. Because it just sits better in your mind to say the odds are 423 to 577 as opposed to saying, oh, the odds are 0.423 to 0.577. You know, this is kind of awkward, you know, to leave decimals over decimals. All right, so we don't really like to do that. All right. Okay. All right. Now, here's another formula that relates probabilities to odds. If the odds in favor of some event E occurring are A to B, where A represents the number of favorable ways or outcomes that yield event E, and B represents the number of unfavorable outcomes that do not yield event E occurring, then the probability that event E will occur is going to be equal to A divided by A plus B. So this formula enables you to go from odds back to probabilities. These formulas here enable you to go from probabilities back to what? Back to odds. Is this making sense here? So these formulas take you from probabilities back to odds, whereas this formula takes you from odds back to probabilities. So, you know, we can now go in both directions. You know, given odds, we can recover the equivalent probability, or given a probability, we can recover equivalent odds. So here's an example. According to the National Safety Council, the odds of dying due to injury at some point in your life are about 10 to 237. Find the probability of dying from an injury. So they want us to convert the odds of dying from an injury, which is 10 to 237, to the probability of dying from an injury. Well, we can use our formula. Notice there's 10 favorable outcomes that yield a death from an injury, and there's 237 unfavorable outcomes that yield that you will not die from an injury. So therefore, our A is like 10 and our B is like 237. So therefore, to compute the probability that, you know, anybody will die from an injury is to take A and divide it by A plus B. So that's going to be 10 divided by 10 plus 237. 10 divided by 10 plus 237 is 10 over 247. That's the probability now of dying from an injury, which is 0.040. So notice the odds are a little different than a probability here, okay? The odds of dying from an injury are 10 to 237. The probability of dying from an injury is 10 to what? 247. That's because, again, odds compare the number of favorable ways an event can occur to the number of unfavorable ways that an event could occur. Whereas a probability basically compares the number of favorable ways an event can occur to the total number of outcomes that could occur on any given trial of an experiment. So there's a difference in the comparisons in these ratios. That's why they're different. Odds versus probabilities. Notice the difference there, okay? All right. Now, I have a question for you. Suppose I gave you the probability of dying from an injury is 10 over 247. How could we convert this probability back to odds? Well, the odds of dying from an injury would be equal to the probability of dying from an injury, which is 10 over 247, divided by 1 minus the probability of dying from an injury, 1 minus 10 over 247. And therefore, we're going to have 10 over 247. Now, 1 minus 10 over 247, 1 is another name for 247 over 247. So 247 over 247 is 1 minus 10 over 247. And what's 247 over 247 minus 10 over 247? That gives you what? That gives you 237, right? 237 over 247. Well, ladies and gentlemen, how does this reduce? Well, it's a well-known fact that if you have a complex fraction where you have A over B over C over B, there's a quick way to simplify this if you just remember the shortcut. You see these B's here? The B's drop out, and you're left with A over C. That's a little shortcut for simplifying a fraction over a fraction where the denominators are the same. See that? The B's drop out, you're left with A over C. So 10 over 247 over 237 over 247, the 247s drop out, and we're left with our odds of 10 to 237. So I've shown you how to go backwards from a probability, how to go to the equivalent odds. Okay? So the odds of dying from an injury would be 10 to 237. The probability of dying from an injury would be 10 to 247. Are we seeing how we're able to navigate back and forth between probabilities and odds just by using the appropriate formula?
That was pretty bad.
But the key is you need to just remember the what? You got to have the formulas here, right? You got to know this formula. This enables you to go from odds back to a what? Probability. And these formulas here enable you to go from odds back to what? Back to a, I'm sorry, enables you to go from a probability back to a what? To odds, right? So if nothing else, you know, you want to memorize this formula here that takes you from probabilities back to odds. And this formula here takes you from odds back to probabilities. So just by knowing those two formulas, we can hopefully navigate back and forth between odds and probabilities. And it just takes a little bit of practice to get used to these formulas. And I'll give you, you know, ample practice. But obviously you have to know those formulas, you know, to have a chance here. All right. All right, ladies and gentlemen, let's turn our attention away from the relationship between probabilities and odds now. Well, let me see. Let me see here. Tell you what, let's go do a couple problems in our textbook. We'll come back to expectation. All right, so let's go to our textbook here and see if we can do a couple of these problems that relate probabilities and odds. All right, so these problems are going to be coming from section 10.6 in our textbook. 10.6 is entitled Odds and Expectation. Okay. And again, feel free to, look down through this section. You can also take a look at some of the examples that are laid out. Although a lot of the examples that are in your section, I've noticed, occur on the PowerPoint. Okay. All right, ladies and gentlemen, we're going to try one here. Number 7. Actually, I'll do number 9, and I'll have you back up and do number 7 for classwork. They want us to find the odds in favor of and the odds against each event given the probability. So like in problem number 8, they give us the probability that event B will occur as 1/9. That's a probability. That's not odds, okay? They want us to convert this into odds of event B occurring and also the odds of event B not occurring. So I'm going to do number 8. All right. So therefore, they tell us that the probability of some event B occurring is 1/9. This is the probability. And they want us to find the odds of event B occurring. Well, according to our formula, how do we go from, a probability back to odds? Well, this is going to be equal to the probability of event B occurring divided by 1 minus the probability of event B occurring, according to our formula. So therefore, this is going to be equal to 1/9 over 1 minus 1/9. Did I see that there? I'm using the formula from the handout, the PowerPoint. All right, so this is 1/9. What's another name for 1? If I am to subtract 1/9 from it? Another name for 1.
9/9.
Yep, why not call it 9/9? Therefore, we have 1/9 over what? What's 9/9 minus 1/9? 8/9. So, ladies and gentlemen, how does this simplify? 1/9 divided by 8/9. What shortcut can I take? Anybody remember? Look, if you can't remember, then you're gonna have to write it as 1/9 divided by 8/9, which means 1/9 times the reciprocal of 8/9, which is to say times 9/8. The 9s cross reduce out, and you're left with 1/8. What was the shortcut in going from here to here, though? Instead of having to go through all this, I could just cancel the what's out. The 9s drop out. Do you agree? And we're left with 1/8. Shortcut. See it? So, ladies and gentlemen, the odds of event B occurring would be 1/8. 1/8 odds. Questions: how I converted the probability of event B occurring to the odds of event B occurring using our formula. Everybody see that there? So it's wise to know this formula, obviously. Okay. So again, the odds of event B occurring would be what? 1/8. So like if we conducted this experiment, whatever it is, let's say 9 times, we would expect event B to occur 1 time, and we would expect some other event to occur, what, 8 times? Or we would not expect event B to occur 8 of the 9 times. We would expect event B to occur 1 out of the 9 times, and we would not expect event B to occur 8 out of the 9 times. All right. So what would be the odds of event B not occurring? What do you think? How can I use the odds of event B occurring to determine the odds of event B not occurring? What do I got to do? Simple thing. What do you think? Take this and just what?
Flip it.
Flip it. The odds of event B not occurring would be 8 to 1. 8 to 1 odds. There you go. Or as a fraction, you know, would be 8 over 1. That's it. So the odds of event B occurring would be 1 to 8. The odds of event B not occurring would be 8 to 1. Questions how I converted this probability into odds of the event occurring or of the event not occurring. Any questions how we did? Do you think you're ready to try one like this?
No.
Convert the prop. What's that? Was that yes or no?
It was a no for me.
No. No. Okay. Well, maybe I might want to work another one out, do you think, or what?
Yes, please.
Okay. Well, let's go back to our textbook and see what other one we got going on here. I'll do number 10. The probability of some event D occurring is 7/10. They want us to determine the odds of event D occurring. So again, we'll use our same formula. So the probability of some event D occurring is 7/10 or 70% chance. What would be the odds of event D occurring? Well, the odds of event D occurring would be equal to the probability of event D occurring divided by 1 minus the probability of event D occurring, just using the same old formula. Same old formula that we used above here. Okay. So what is the probability of event D occurring? Well, they told us it was 7/10. Divided by 1 minus the probability D occurring would be 1 minus 7/10. Well, that's 7/10 over what? What's another name for 1? 10 over 10? So that's 7/10 over what's 10/10 minus 7/10? That would be 3/10. 3/10. What can I do with the tens? Shortcut.
Cancel them.
Yeah, just get rid of them. And your answer is 7 over 3. Or your odds of event D occurring would be 7 to 3 odds. Sometimes they express it this way also, 7 to 3. They literally write the word 2 in there. T-O, not T-W-O. 7 to 3, 7 to 3, 7 to 3. All these mean the same thing. Those are the odds of event D occurring. Okay? 7 to 3 odds. So there's 7 favorable ways that would enable event D to occur, and there's 3 unfavorable ways that would prevent event D from occurring. Make sense? So if I was to conduct this experiment, whatever it is, 10 times, I would expect of the 10 trials, event D to occur 7 times. Of the 10 trials, I would expect event D to not occur 3 out of the 10 trials. Okay. All right. So what's the odds of event D not occurring then? What would it be?
3 to 7.
3 to 7.
3 to 7. It's as simple as that. So the odds of event D not occurring is equal to the reciprocal of this. Just flip it upside down, 3 to 7. Or, 3:7. Or, you could say 3 to 7. All right. There you go. With this second example, is it a little bit clearer as to how we convert the probability of an event occurring into the odds of the event occurring or the odds of the event not occurring? Is it a little bit more clear now?
Yes.
All right. Now I would like you to try one for classwork all on your own now. All right. I'll give you a hint. It works exactly the same way as that example and also this example. No difference. All right. So for classwork number 1, I want you to do problems 7 and 9. 2 of them, 7 and 9. I want you to compute the odds of these events occurring and the odds of the events not occurring, 7 and 9. Go ahead and do that. Classwork 1. So for number 7, we know the probability of some event A occurring is 7 to 8. What are the odds of event A occurring? Well, that would be the probability of event A occurring divided by 1 minus the probability of event A occurring, which is to say 7/8 over 1 minus 7/8, which is 7/8. Another name for 1 is 8 over 8. 8/8 minus 7/8 is 1/8. You can just drop these 8s out, and we're left with a 7 to 1 odds. Do you agree? So the odds of event A occurring would be 7 to 1 odds. The odds of event A not occurring would be 1 to 7 odds, expressed any one of those 3 ways. Did anybody get this?
I did.
Yes.
All right, so we're having some success now in moving from probabilities to odds. Number 9, the probability of some event C occurring is 5 over 11. Therefore, what would be the odds of event C occurring? Well, that's the probability of event C occurring divided by 1 minus the probability of event C occurring. That's 5/11s divided by 1 minus 5/11s, which is 5/11s over, I expressed 1 as 11 over 11. 11/11s minus 5/11s is 6/11s. The 11s cancel out if you want to take a shortcut, and the odds of event C occurring would be 5 to 6 odds. The odds, therefore, of event C not occurring would be 6 to 5 odds. So is this making any sense here, ladies and gentlemen, how we're going from probabilities to odds? Making any sense just by using that same old? Okay.
So far.
Let's go backwards now. Let's see if we can go from odds back to probabilities. All right. So now we're going to entertain problems 13 through 18. And in these problems, it says, find the probability of each event given the odds of occurrence of the event. I'm going to do number 14. And so what they want us to do is take the odds of some event occurring, which is 9 to 13 odds. They want us to convert that into the probability of that event occurring. Now, they did not give a letter to represent the event that's occurring. You can call it anything you want. Any letter, you can use any letter you want. I'm going to use a letter E for event, okay? So in other words, from problem number 14, they give us the odds of some event E occurring is equal to 9 to 13 odds. Okay, 9 to 13. How do we convert the odds of this event occurring into the probability of its occurrence? Okay, now we need to recall our formula. And the formula goes like this. The probability of some event E occurring is equal to A divided by A plus B, where, okay, A is the number of favorable ways event E can occur, and B is the number of unfavorable ways event E cannot occur. In other words, the odds of event E occurring would be expressed as A to what? B. So look at, to go from the odds of occurrence of some event A, which is A to B, to the probability of that event occurring, we simply use this formula, A divided by A plus B. So what's our A here? Our A is what? 9, and our B is what? 13. Therefore, it's just a simple matter. The probability that event E will occur is equal to A, which is 9, divided by A plus B, divided by 9 plus 13. Therefore, 9 over what? 22 is the probability of event E occurring. 9 over 22 is the probability. So I went from the odds in which some event E can occur, which is 9 to 13, to the probability of that event E occurring, which is 9 over 22. Do we see how using that formula, I was able to go from odds to probability? So it really comes down to, obviously, you're going to have to either memorize these formulas or have them what, handy. Do you agree? When you go to Alex, correct? You're going to have
Yes.
those handy in order to go back and forth between odds and probabilities. All right. But that's the formula you use to go from A to B odds to the probability being A over A plus B. Good. All right. Having seen this one golden example, do you think, ladies and gentlemen, that you can emulate this with a problem? Will you try one out? Same formula, same approach.
I think I can do it.
Just different numbers. All right, so let me have you do number 13 for classwork number 2. I want you to convert the odds of some event, and maybe you could call the event E, so we're all on the same page. The odds of some event E occurring is 5 to 8. What would be the probability of that event E occurring? Go ahead and compute the probability, number 13. Converting odds to probabilities. I tell you what, and while you're at it, see if you can do 15 too. Compute the probability of against some event occurring. Okay, or in other words, the probability the event E will not occur from the odds of it not occurring being 6 to 5. Okay, so do 13 and 15. Convert those odds into probabilities. Okay, so they give you the odds in favor of an event occurring or the odds of an event not occurring. And they want us to convert these odds into probabilities. Well, I've shown you the formula in general there. If the odds of event E occurring is A to B, then the probability of event E occurring is going to be A divided by A plus B. All right, that's always the formula used to convert from odds to probabilities. So using that formula, we're going to answer questions 13 and 15. So therefore, if the odds of event E occurring are 5 to 8, then the probability of event E occurring would be 5 over 5 plus 8, or 5/13. Did anybody get that? Correct.
I did.
Now, the odds of some event E not occurring is 6 to 5. Therefore, the probability of event E not occurring would be 6 over 6 plus 5, or 6 over 11. That's the probability that event E will not occur. Okay? Did we get that probability there?
Mm-hmm.
Okay. All right. Now that we have a good understanding as to how to navigate between odds and probabilities, depending upon, it depends obviously on what formula you use. That will take you to from one to the other. Let's try number 24. You can call this classwork number 3. I would like you to do all of these questions for classwork 3, A through E. Suppose we roll only one fair die. Find the resultant odds of these things occurring here, okay? For E, what's a prime number as far as a die is concerned? Well, there's only 6 numbers, correct, that concern ourselves with a die. And of the 6 numbers, 1 through 6, which of them are prime numbers? Well, that would be 2, 3, and 5. Those are the prime numbers on a 6-sided die. All right, see if you can answer questions A through E. Compute those odds. Assuming this is a fair die, okay? If you're still hung up, I did do A for you. What's the odds of rolling a 3 on a fair die? Well, how many number of favorable ways yield a 3? There'd be only one favorable way, correct? How many unfavorable ways do not give us a 3 when we roll a die? There's 5 unfavorable ways. Therefore, the odds of rolling a 3, okay, would be 1 to 5 odds. 1 to 5. All right, you do the rest of those now. All right, so let's see if we can begin to look at a couple of these here. So what's the odds of rolling a 3? Well, how many favorable outcomes yield a 3? There would be 1, correct? How many unfavorable outcomes would not yield a 3? Well, there's 5 unfavorable outcomes that would not yield a 3. So the odds of rolling a 3 would be 1 to 5, 1 to 5 odds of getting a 3. What are the odds of rolling a 6? Well, there's 1 way to roll a 6 versus 5 ways of not rolling a 6. So the odds would be 1 to 5.
You took the number.
All right. What's the odds of not getting an odd number? Well, how many ways can you not roll an odd number? In other words, how many favorable ways are there that do not yield an odd number? There would be 3 ways, rolling a 2, 4, or 6. Versus the number of unfavorable ways of not getting an odd number would be 3 ways, rolling a 1, 3, or 5. So the odds of rolling an odd number would be 3 to 3 or 1 to 1 odds. Now, the odds of not getting an even number, ladies and gentlemen, if you're a little uncomfortable in computing the odds of not having something occur, think of it as being the reciprocal of the odds of having the event occurring. It works the same way. So if you don't want to compute the odds of not getting an even number, consider this as computing 1 over the odds of getting an even number. Maybe that sits better in your mind. So what's the odds of rolling an even number? Well, how many ways can an even number occur? That occurs if you roll a 2, 4, or 6, so 3 ways. Over how many ways can you not roll an even number? 3 ways. You roll a 1, 3, or 5. So 1 divided by 3 over 3 is really 1 divided by 1, or 1 to 1 odds, or 3 to 3 odds, we would say, or 1 to 1 odds of not getting an even number. Okay. All right. Did we have any success on those there? All right, I would like to try to do just one more out of your textbook. And I'm going to do this one. I'll do number 25 here. It says Steve shuffled a deck of 52 cards and asked Sally to draw 1 card to start a magic trick. Find the odds in favor of getting a queen. Okay. So what's the odds in favor of, this is 25A here. What's the odds in favor of getting a queen? Well, how many queens are there in a deck? There's 4 queens. Do you agree? A queen of hearts, a queen of diamonds, a queen of spades, and a queen of clubs. Versus how many ways to draw a card that's not a queen? 48 cards that are not queens. So here's the odds of drawing a queen, 4 to 48 odds. Or you could reduce this down to 1 to 12 odds. right? 1 to 12 odds. What's the odds in favor of getting a face card? Well, how many face cards are there in a deck? You have Jack, Queen, King of 4 different suits, correct? Hearts, diamonds, spades, and clubs. So 3 face cards per suit times 4 suits is 12 face cards. So there's 12 ways to draw a face card. Out of how many ways to not draw a face card? That would be 52 minus 12, which is going to be what? 40 ways of not drawing a face card. Therefore, your odds of drawing a face card would be 12 to 40 odds, which you could reduce this down by 4, down to 3 to what? 3 to 10 odds. Making sense here? How many ways of not getting a club? Well, how many ways can you draw a card that's not a club? In other words, how many cards are in a deck that are not clubs? Well, there's 13 clubs, correct? Ace through king. So that means there must be 52 minus 13, which is going to give you 39 cards that are not clubs. So the odds of not drawing a club would be 39 to what? 39 to what? 52 minus 39 is what, 13? 39 to 13 odds? 39 to 13 odds of not drawing a club from a deck of cards. And this reduces down by 13 down to what? 3 to 1? 3 to 1 odds of not drawing a club from a deck of cards. What's the odds of drawing an ace? How many aces are available? There's 4 aces available. And there is 52 minus 4 or 52 minus 4 or 48 unfavorable cards that would not yield an ace. So your odds of drawing an ace would be 4 to 48, which reduces down to 1 to 12 odds. So what's the odds of not drawing an ace? It would be 12 to 1 odds, correct? So what's the odds of getting a black card in a deck? Well, you got 13 spades, you got 13 clubs. That's 26 cards of the 52 are black, and 26 of the 52 cards are red. So the odds of drawing a black card from a standard deck of cards would be 26 to how many cards are unfavorable in yielding a black card? That would be 52 minus 26, or 26 cards are red cards. So the odds of drawing a black card would be 26 to 26 odds, better known as 1 to 1 odds. Or, ladies and gentlemen, the probability of drawing a black card from a deck of cards would be 1 over 1 plus 1. Or the probability of drawing a black card would be 1/2, or 50% chance. That makes sense. Since half the deck is black, half the deck is red, correct? Is this making any sense here? Any nods? All right, we got to wrap this up now. We got to go back to our PowerPoint, ladies and gentlemen, and look at what is called expected values. All right, another concept related to odds and probability is something called expectation or expected value. Expected value is used to determine the results that would be expected over the long term or long haul of a probability experiment. It is used not only for games of chance, but also is used frequently in areas in the insurance industry. Expectation is used in management and engineering and other various fields. The key element is that the events in question must have numerical outcomes. All right. Suppose we play a game. We pay $1 to roll 2 dice. If you roll a total of 5 or a 6, you get your $1 back plus 2 more just like it. If not, you get nothing. Find the probability of winning the game. Well, and we're rolling 2 dice, and how many ways can you roll the sum of a 5 or a 6? Now, we've seen this in our textbook way back, where they had a table laid out, and there's 36 different outcomes that could occur, 36 different sums that could occur when you roll 2 dice, okay? And of the 36 different sums, how many sums yield a total of 5 or a 6? Well, instead of going back to that table and creating a table, let's just save a little bit of time. And just trusting me when I say there are 9 outcomes of the 36 that yield a sum of 5 or a 6. Therefore, there's on the probability of rolling a sum of 5 or a 6 when you roll 2 dice is 9 over 36, or 1/4 chance, or in our minds, we know that is 25% chance. Okay? If you play the game 100 times, suppose we play this game 100 times and rolling these 2 dice, on average, how many times would you expect to win? In other words, on average, of the 100 rolls of these 2 dice, how many times would you expect to roll a sum of a 5 or a 6? Well, when we play the game once, we've seen that the probability of winning would be 1/4 chance, correct? Therefore, if we play this game 100 times, ladies and gentlemen, we would expect to win 1/4 times 100 times, or 1/4 of 100 would be 25 times out of 100 we would expect to win. So we would expect to win 25 out of the 100 games if we play this game over and over again. You understand how we got 25? 1/4 times 100. What would be the total amount won or lost? Well, if we roll a sum of 5 or a 6, ladies and gentlemen, what do? We win $2. Do you agree? But if we don't roll a sum of 5 or a 6, we lose $1 because we got to pay $1 to win this game, to play the game, correct? So we can compute what's called an expected value or expected earnings of playing this game over many, many, many times. And notice that we would, if we played this game 100 times, we would expect to win 25 of the 100 games based on what we did in the previous problems. In other words, we would expect, ladies and gentlemen, to win. If we win 25 out of 100 games, we'd expect to win 25 times $2, or we'd expect to win $50. Because remember, when we win $2. All right? We win $2. But there's a chance we could lose. And if we play this game 100 times, we would lose the game 75 out of 100 times, which means that we would lose 75 times $1, or we would lose $75. Therefore, if we played this game 100 times of rolling these 2 dice, we would expect our earnings or winnings to be minus $25. Meaning, ladies and gentlemen, that if we play this game 100 times, we expect to lose $25. So I have a question for you. If this is a game that's played at a casino, let's say, who does it favor? The player or the house? Does this game favor the player or the house?
The house.
Definitely the house. You see that? Okay. And you can bet that casinos do their math and do their homework, and they actually hire mathematicians, ladies and gentlemen, to ensure that the house makes a profit on a daily basis. I'm not saying you never win at a casino, but I'll tell you one thing. The longer you play the games at the casino, okay, the greater chance exists for the house to win and for you to lose. That's a guarantee. All right, so how do we compute expected values? To find expected values, we simply multiply the numerical results of each outcome by the corresponding probability of that outcome, and then we add these products together. All right, let's try another example. Suppose when we roll a single die, we want to find the expected value of the outcome and describe exactly what that means. Well, when we roll a die, ladies and gentlemen, one of 6 faces could occur, correct? We could roll a 1, 2, 3, 4, 5, or 6. What's the probability of rolling each of those faces? It would be a 1/6 chance, assuming it's a fair die. So if we were to roll this die, okay, over many, 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 many trials, suppose we're to roll this single die maybe like 500,000 times, and we kept track of what face came up. We would expect on average for all these faces to average to about 3.5. Now, how did we get that? Well, when we roll a die, we could roll a 1, and the probability of that occurring is 1/6. Plus, we could roll a 2 times the probability of its occurrence is 1/6. Plus 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. We would say the expected value that is rolled on this die, if you were to roll this die over many, 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 many trials, the average face that we would roll on this die would be 3.5. Now, is that saying that when you roll this die on any given time or trial that you're going to roll a face of 3.5? It's not saying that. The expected value is an average, ladies and gentlemen. It's the average value that you would expect to occur, okay, when you play the game for many, 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 many trials, okay? It's an average. So on average, we would expect to roll a face of 3.5 if we played this game many times, all right? All right. Here's another game. The prize in a raffle is a flat screen TV valued at $350. So if we win this prize, we win $350. But 1,000 tickets are sold, and to play the game, you have to pay out $1. So I have a question, ladies. If I won this TV, did I win $350? What's my net winnings? My net winnings. If I play this game once and win the TV. Yeah, I won a $350 TV, but I had to lay out how much money to play the game.
$1. So your net winnings are $349.
Yeah, my net winnings would be $349. If I do not win this game, though, what's my net winning then? If I do not win the game on one play, my net winnings would be what? -$1. Do you agree? I'm out $1. What's the expected value or the expected winnings if you buy one ticket? Let's make a table. Suppose, ladies and gentlemen, we call X, the variable X, they call it a random variable in probability. Suppose we call this random variable X the gain that we experience. If we win, we have a net gain of $349 because we won a $350 TV, but we had to lay $1 out to play the game. That would be our net winnings. If we lose the game, we have a net winnings of -$1. Now, what's the probability of winning this TV? Well, there's 1,000 tickets that were sold, and there's only one ticket that's a winner. So your probability of winning this TV is 1 out of 1,000. That's the probability of winning the TV, right? 1 out of 1,000. Or, ladies and gentlemen, we would say the odds of winning this TV would be what? 1 to what? 999? The odds of winning this TV would be 1 to 999. The probability is 1 to 1,000. What's the probability of losing this game? Oh, that would be 1 minus 1 over 1,000, or to say 1,000 over 1,000 minus 1 over 1,000 would be the complementary probability, which is 999 over 1,000. That's the probability that we lose the game when we buy one ticket. So let's compute the expected net earnings when we play this game once. That's easily computed by taking our net earnings and multiplying it by the probability of its occurrence. So we take $349 times the probability of that occurring, which is 1 over 1,000, plus -$1 times the probability of that occurring, which is 999 over 1,000. So if we were to play this game, ladies and gentlemen, many, 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 many times, all right, if we were to play this game over and over and over and over again, many, many, many times, on average, we would be expected to lose, okay, per play, we would be expected to lose 65 cents, okay, on average. So that's just per one play, correct? We would expect to lose 65 cents. So obviously this game favors what? It looks like it might favor the house, right? So it doesn't look like it favors the player. In fact, anytime your expected winnings is negative, that means the game favors the house and does not favor the player. For a game to favor a player, the expected earnings would have to be a positive value, right? All right, here's another game. Suppose 1,000 tickets are sold at $1 each for 4 prizes: $100, $50, $25, or $10. What is the expected value if you buy 2 tickets? What would be your expected winnings if you buy 2 tickets? In other words, if we were to play this game many times, on average, what would be our expected earnings or winnings? Well, to answer this question, in order to determine, our expected winnings in playing this game twice, we should first of all find out what our expected winnings would be if we play the game just one time. So to do that, we make a table. X again represents the gain of playing the game, our net winnings, if you will. If we win $100, our net winnings would be $99 because we had to lay out $1 to play the game. If we win the $50 prize, our net winnings would be $49. We win the $25 prize, net winnings would be $24. And if we win the $10 prize, our net winnings would be $9. If we lose $1. Now, what's the probability of winning the $100 or having the $100 winning ticket or prize? Well, that's 1 out of 1,000 because there's only 1 out of 1,000 tickets that have the winning prize, $100. What's the probability of winning the second prize? Second place prize, you could call it maybe $50. Well, there's only 1 ticket that has a $50 winner on it, 1 out of 1,000. There's 1 out of 1,000 tickets that have the $25 and the $10 winner also. So there would be 1,000 minus 4 tickets, or 996 tickets. That would be what? The losing ticket, correct? In which case we would lose $1. We can now compute the expected net earnings of playing this game. All you got to do is take the net earnings and multiply it by its probability of occurrence and add all those products together. So let's do this. 99 times 1 over 1,000 plus 49 times 1 over 1,000 plus 24 times 1 over 1,000 plus 9 times 1 over 1,000 minus $1 times 996 over 1,000. So if we play this game one time, our expected net earnings would be to lose about 82 cents. So therefore, ladies and gentlemen, if we play this game 2 times or buy 2 tickets, we would expect to lose about $1.63 on average, okay? So if we were to play this game many times, buying 2 tickets at a time, if we kept a running average of our net winnings, we would expect that average to be minus $1.63 per play on average, okay? And this is emphasizing, as I already indicated, if the expected value in a gambling game is 0, then the game is said to be a fair game. So in other words, to be a fair game, your expected gain of playing this game would be 0. If the expected value of the gain of the game is positive, then the game is in favor of the player. If the expected value of the game is negative, then the game favors the house, okay? All right, so you can bet, like, I'll stop and think. I mean, if you're a casino, you want to stay in business, correct? So you want to cut a profit. Everyone wants to make a profit. So you can bet that in general, they have geared all their machines and all their games, and they've had maybe a team of mathematicians basically go through all the probabilities and all the expectations of all the games, and they made sure that in general, that all of the expected values of all the games that are in the house favor the house. in order for the house to make a profit. Those people that they hire that have math degrees that do all these number crunchings, they call them actuaries, okay? And actuarial science is a very lucrative job. If you get an undergraduate degree in mathematics, you could take a battery of exams and become a certified actuary. Actuaries work for casinos, they work for insurance companies, they also work for like shipping industries and also amusement parks. Actuaries, I think now are called more so, they're called, what do they call them? Logistics. They call that logistics, essentially. So I think the name actuarial science has been transformed into the name logistics science, okay? But those are people that have math degrees that basically analyze data in order to determine, required outputs for like companies to stay in business or to make a profit. So again, the key is like if you go to a casino, if you win from a machine, let's say you win, sizable amount of money from a slot machine. It's a given, ladies and gentlemen, that if you reinvest those winnings in a slot machine and keep playing to try to win more and more and more and more and more, if the longer you keep playing and reinvesting your winnings, it's guaranteed that the house will get the money back. That's a guarantee, okay? So word to the wise, if you win on a slot machine, you might want to save the bulk of the winnings out and just reinvest a small amount if you want to keep playing. That's word to the wise, all right? Okay, let's go to our textbook here. See if we can have some fun. All right. Okay. So we will try to do a couple of problems out of our textbook in section 10.6 involving expectations. So we don't have a ton of time left. All right, so like I said, yeah, we don't have a ton of time left. And as a result, we're going to have to use our time wisely here. Let's go down here. All right. Now, problem number 19, they give you the value of a random variable, which could be 6 or 2 or 4 for some sort of probability. Like you can think of it as being like a probability game or something. And they give you the probability of that value occurring. In other words, the probability that a random variable takes on a value of 6 would be 1/5. The probability that a random variable takes on a value of 2 would be 2/5. The probability that a random variable takes on a value of 4 would be 2/5. What would be the expected value of the probability experiment with these outcomes and these probabilities? So all you got to do is take the value of the random variable and multiply it by its probability of occurrence, and then just add those products together, and you will have what's called the expected value. So let's see if you can do this problem. Throw it into classwork. Just throw it into the classwork. You take 6 times 1/5 plus 2 times 2/5 plus 4 times 2/5. Crank it out, add those together. You have the expected value of our random variable if this game was to be conducted over many, many trials, okay? So we want to try to compute the average value we would expect a random variable X to assume upon playing this game over many trials. So see if you can compute that expected value. Number 19. So the expected value of our random variable is going to be the value that the random variable is assigned or takes on times its probability of occurrence, or times the probability that it is assigned that value. So you got to take 6 times 1/5 plus 2 times 2/5 plus 4 times 2/5. So this gives you 6/5 plus 4/5 plus 8/5. 6 plus 4 is 10 plus 8 is 18. So 18/5. And that's going to be 3 and what? 3/5, which is 3.6. Did anybody compute that for the expected value? 3.6.
Yes.
Okay, that's the expected value. All right, let's go on down to number 51. A cash prize of $5,000 is to be awarded at a fundraiser if 2,500 tickets are sold at $5 each. Find the expected value of buying one ticket. So on average, ladies and gentlemen, if we were to play this game many times and buy one ticket, on average, what would be our average net winnings or net earnings for this game here? Go ahead and see if you can compute that expected value, number 51. All right, so for this problem here, I made a little table to help me organize my information. If I win the jackpot, win the prize, I win $5,000, but it took $5 to play the game. So that means my gain would be $4,995. The probability of that occurring is there's only one out of the 2,500 tickets that has this winning jackpot. So your probability of winning is 1/2,500. If you lose the game, you're out $5, and the probability of that occurring is 2,499 over 2,500. The expected net earnings then, ladies and gentlemen, can be computed by taking the net winnings and multiplying by the probability of that happening, and then adding the products together. So your expected winnings or net winnings would be minus $3. That means that you have a better chance of losing money at this game than you do of winning money. Okay, and to make things, simple in layman's terms. So it looks like if you were to play this game many times, on average, you would lose about $3 per play. Okay. Did anybody compute that expected value?
Yes.
Okay, just one more. We got time for just one more. Number 55. Melinda buys one raffle ticket at the Spring Fling. Since there is one $1,000 prize, one $500 prize, and five $100 prizes, there were a total of 1,000 tickets sold at $3 each. What is Melinda's expectation if she plays this game once? Okay. So go ahead and see if you can compute the expected value for number 55 by playing this game. All right, so again, a table really helps. Your net winnings, if you win the grand prize, if you will, you win $1,000, but you had to pay out $3 to play the game. Your net winnings would be $997. That occurs with a probability of 1/1,000 because there's only one winning ticket of 1,000 that has that prize. If you win the $500 prize, your net winnings would be $497, and there's 1/1,000 probability of winning that. And there's 5 $100 winning prizes, in which case you'd win $97, your net winnings, and that would occur with a probability of 5/1,000. You stand a 993 over 1,000 probability of losing $3. So computing the expected value, you just take the product of your random variable value times its probability, and you add all these together. This times this, plus this times this, plus this times this, plus this times this. Run it through the calculator, and you get an expected net winnings of -$1. -$1. Okay. So, on average, if you were to play this game many, many times, you would expect to lose per play $1. Anybody get that there?
Just one question. Where did you get the 993 from?
There were 1,000 tickets sold. 5 + 1 + 1, 7 tickets are winners. Do you agree?
Yeah.
That means 993. 1,000 minus 7 or 993 tickets are what losers. Does that make sense, sir?
Oh, okay.
That's how I got there. Yep.
Okay.
All right, ladies and gentlemen, I'll stay on the line for a couple of minutes if you have any questions or comments. If not, hopefully I'll see you in a couple of days. Have a nice day.